Hello. Now we will do the another property of conductor. And in this property, we learn about how the potential inside the conductor is same. So this is our conductor. And we want to prove that, let's assume I'm taking 3 points, 1, 2, 3. I'm calling potential here is V1, and here V2, and here V3. And the property is that V1 will be equals to V2, and that will be equals to V3. Or you can say for any point inside the conductor, when you calculate the potential, that comes out to be same. So for all points inside the conductor, potential is same. That's the thing. That's the property. Now let's prove it. So we already know about the conductor something. Like if you talk about the conductor, electric field for all inside point for the conductor is 0. Meaning if you go for inside points, electric field everywhere is going to be 0. Okay. Now let's assume the 2 points here. I'm calling it A and B. There are two general points inside this conductor. So A and B, there are these two general points, and the position vector of B with respect to A I am defining as dr. Okay. So A and B I have taken as a random points, and the position vector of B with respect to A is dr. Okay. So if potential at B minus potential at A divided by dr, if you see, that will be equals to electric field. If A and B are very nearby, and this thing we can write it as, sorry, it is minus, this thing we can write it as dV upon dr. Okay. So dV upon dr is E. Inside for all points, if you calculate the potential gradient, this value is equals to potential gradient, meaning as you move from one point to other point, how the potential varies. So potential gradient is equals to minus of E mod, obviously. That's the relationship. This we get from the Coulomb's law, modification of Coulomb's law. Now see, if you use this result is for all inside points, and I'm talking about the inside points only, meaning where the free particles are available. Meaning I'm not talking about the cavity, meaning A and B will not be in the cavity. They will be, A and B points will be inside the conductor where the free electrons can move. Okay. Since for all inside point this electric field is 0, and if electric field for all inside point is 0, in that case you can say dV upon dr will also be 0 for all points. So differentiation of, or we can say the gradient of potential is 0. And if the gradient of potential becomes 0, it means the potential is constant. So for all inside points, in case of conductor, the potential is going to be same. Okay. At the same time, since we already know, because this thing happens only at equilibrium, so all these results are only for the equilibrium. So see, at equilibrium, what happens? These electrons, they stop moving. So ultimately, before equilibrium, they were moving, and we know that electron moves from higher potential to lower potential. So if there will be some potential difference, then at one point there will be higher potential, at other points there will be lower potential. The moment you find any 2 points in this conductor where there is a potential difference, electron will start moving, and they will move till there is an equal potential at each and every point inside this conductor. So this is a mathematical proof, and you can see from the concept of this motion of electron moves from higher potential to lower potential. They will keep moving till there is a potential difference. And when they are not moving, meaning at equilibrium, there will be no potential difference. So that way we can understand this thing. So the second statement, or this one more property we have discussed, that is regarding the potential inside all points. In case of conductor, potential is always same after achieving the equilibrium state. Okay. Thank you.